So now we get the pleasure to go to our last portion of our metabolism. So we've already discussed glycolysis. We've discussed citric acid cycle. Now we're going to take those electrons from the NADH and the FADH2 from glycolysis and the citric acid cycle, and then take them to the electron transport chain and make ATP through oxidative phosphorylation. It's the last chapter in our metabolism that we're going to study in this one catabolic metabolism of glucose. So you can see we're going to make 32 ATP from this. So from these NADHs and FADH2s. So where does this happen? As the picture shows, in the matrix. Yeah, in the mitochondrial matrix. All right. We're going to first study our background. We're going to review redox reactions. Make sure that we fully understand that. I mentioned last time, before starting this chapter, you really need to review your standard reduction potentials if it's been a while since you've taken Chem 2. We're going to then discuss electron transport, the components, how we inhibit it, and looking at those inhibitors, that's how we figured out how electron transport works. We're going to see how we couple electron transport to oxidative phosphorylation, making ATP. And it's the chemiosmotic theory describes how we synthesize ATP and how we can uncouple electron transport from making ATP and kill people. And then there's NADH that is made in the cytosol from glycolysis. How do we get that to where electron transport happens? So that's where we're going to end. But in a nutshell, electron transport chain is a series of electron carriers in the inner membrane of the mitochondria. What they're going to do is they're going to pass electrons from one another until it finally reaches oxygen. So think about a battery, a current. That's electrons flowing. Your inner membrane is like a little battery, all right, producing energy. We're flowing electrons through, just like we flow electrons through a wire. But the way we're flowing electrons, instead of along a copper wire, is through these, and I want you to think of them as buckets. All right? We're going to pass electrons from one electron carrier to another, to another, to another. All right? And going from one thing to another, the passing of the electrons, that's what frees energy. So passing electrons from one electron carrier to another, the act of passing it frees energy. And what we use that energy for is to set up conditions to make ATP. We're going to discuss how these, or why the electrons get passed. And that's how we're going to use our standard reduction potentials. Why do the electrons get passed from one bucket or carrier to another? And our standard reduction potential is going to help us understand that. So I said that we're going to use the energy that's being released every time an electron is being transferred to set up conditions so that ATP can be made. And basically what we're going to do is pile up protons in the matrix, or out of the matrix, and we're going to pile them up in such a way that they want to get back. It creates a gradient of high concentration on one side of the membrane and low concentration of protons on the other side. And they want to get back. It's like piling dirt on the top of a hill, and it just wants to roll back down. So we use the energy from passing the electrons to push the protons to one side of the membrane. And we're holding it there. We're holding it there. And then we spring a leak. And that springing of the leak and having those protons coming back, that action of flowing through that channel, that's called ATP synthase. And that channel allows the ATP to be produced. It's like the dams that they make in a in a river. All right, you have all this energy packed up behind a dam. If you spring a leak and you put, don't they put like the turbines behind that get moved by the flowing water? It's exactly like that. That's how I want you to think of it. So the passing of the electrons is just, it's going to be piling that water or the dirt on top of the hill, the water behind the dam, or whatever way you want to think of it. It's packing that energy up. And then the only way that it can get back to where it wants to be even is through ATP synthase. And so the act of traveling through the ATP is what produces the ATP, traveling through the ATP synthase, this little lollipop-looking thing, it produces our ATP. It phosphorylates the ADP to ATP. This requires energy. It doesn't happen spontaneously. All done? Time's over? Time's up? All right. So here you can see, and again, just like I did with the other pathways that we looked at, we're going to go over 500 times. And so this is one of the ways we're going to look at it. There's different levels that you can look at this. We're going to take a little intermediate level. There's some things that we're going to cover and some things that we're not going to cover. So this green is going to be complex 1. This blue is complex 2. This pink, and we're going to forget about this. We're not going to do this part. So just put a little X over it because we're not going to cover that. This pink is complex 3, and this other shade of green, this is blue-green, I guess green-green, is complex 4. The yellow is what travels in between. So in each of these complexes, so this is complex 1, complex 2, complex 3, and complex 4. They're much more complex than they're much more complex than what I'm showing here. But you can see that we're starting out with complex 1 and complex 2 with our reduced coenzymes. And there's a lot going on here. Some of it we know, some of it we don't, where we're going to be passing the electrons along and then passing those electrons to something called coenzyme Q. There's a couple names for this we'll go over. Coenzyme Q. This coenzyme Q accepts the electrons from complex 1 and complex 2 and then carries it to complex 3. So the complex 1 and complex 2 accept the electrons or take the electrons from the reduced coenzymes that we have from our glycolysis and citric acid cycle and passes it on to coenzyme Q. Coenzyme Q carries those electrons to our complex 3, which has a grouping of types of proteins called cytochromes. Complex 3 passes it along, and then there's cytochrome C goes in between complex 3 and complex 4. Complex 4 has a number of things, but one of them is cytochrome A. And then the final electron acceptor is oxygen. All right. So just X out this. We're not going to talk about that. Now, all of these reactions, passing the electrons around, are redox reactions. Remember, acid-base reactions, you pass around protons. Redox reactions, you're passing around electrons. Redox reactions are energy-producing reactions. But it's not ox reactions. It's not re-reactions. It's redox reactions. You have to have a reduction with an oxidation. So something gets oxidized, something else gets reduced. So this is where it's happening. I cut a mitochondria in half. I didn't do that. That would be pretty cool if I cut a mitochondria in half. Anyway, so those reactions, the releasing of the free energy, every time an electron is passed, frees free energy. And what it does is it takes protons from the matrix and puts it into the inner membrane space.
Say that one more time.
Sure, I can say that again. The free energy from passing the electrons from one electron carrier to another is that free energy is going to be used to take protons from the matrix to the inner membrane space. Yes, Amanda?
So right now, the electrons are going against their gradient?
No, right now the electrons are traveling along the inner membrane. So what we have is basically globs, complex, which is a glob of proteins. Complex 1, complex 2, complex 3, complex 4, just lying along this inner membrane, and they pass along that. All right, so they're going through the membrane, and we'll see that in a second. So they're not going from the matrix to the inner membrane space. They're traveling along that membrane. What happens is the byproduct of those reactions pulls protons from the matrix and passes them into the inner membrane space. And we're going to see how that happens. We're going to take a look at each complex and see how it's pulling, why it's pulling protons from the matrix into the inner membrane space. So what that does, when you have the electron transport happening, is it's creating a situation where in the inner membrane space, we have high proton concentration, low pH. Remember, pH, a low pH means high proton concentration. In the matrix, we've been pulling out protons, so there's low proton concentration or a high pH. We get electrochemical gradient. A gradient means it's different on one side than the other. Right? That's what a gradient means. Electro means that there's a charge difference. When you have a charge difference, a separation of charge, you can measure voltage. So if you had itty-bitty voltage, a voltmeter, little tiny baby voltmeter, you could go along your inner membrane and measure a voltage, right? Because you would have more charge in the inner membrane space than you do in the matrix. So you have separation of charge. Electrochemical means the chemical is the protons, right? Gradient means difference. So electrochemical gradient being set up along our inner membrane. That's what I mean. Electro means charge difference, higher charge in the inner membrane space, lower charge in the matrix. The action of passing electrons along the complexes causes protons to move into the inner membrane space. So are we ready to take a review of our electrochemistry? We're going to go way back into Gen Chem 2. You guys ready? No? We're going to start with basics. There's not going to be any student left behind, no matter what your background is, right? No child left behind. All right. Oil rig, Leo goes Gur. You guys remember that? Oxidation occurs when we're losing electrons. Reduction means we gain electrons. I don't know about you, but that's kind of hard for me to remember. I could remember Leo goes Gur, but I like to look at the oxidation number to help me figure out what's happening. Let's take this reaction. Copper 1, because it's 1 plus. Iron 3, because it's 3 plus. Copper 2, because it's 2 plus. Iron 2, because it's 2 plus. So we go from copper 1 to copper 2. The charge, which is equal to the oxidation number, is going up. When you have an oxidation number going up, you're being oxidized. You guys remember that? Those of you that had me for Chem 2, I'm hoping, or there will be tears coming down my eyes.
What did you say?
The oil rig and Leo goes Gur, that's too complicated for me. Is it losing electrons? Is it gaining? How do I know? the way I remember it, because I'm like, okay, going from copper 1 to copper 2, are you losing electrons? You are, but the way I remember it is you're going from copper 1 to copper 2. You're going up in oxidation number. So going up in oxidation number means you're being oxidized. What's happening to iron? You're going from iron 3 to iron 2. Your oxidation number is going down. You're being reduced. Is that easier than oil rig and Leogos-Guard? I think that's a little bit easier to remember. All right, what about agents? They're secret. They work for the other side. It's a secret agent. So if copper is oxidized, what kind of agent is it? Reducing agent. Because in this reaction, copper is causing iron to be reduced. Remember what I said. You don't have an oxidation without a reduction. Right? So my right hand is oxidized, my left hand is reduced. They have to work together. So the oxidized is causing this guy to be reduced. The one that's being reduced is causing the other one to be oxidized because they're happening together. So here, copper is oxidized while iron's reduced. Well, copper is causing iron to be reduced. Iron is causing copper to be oxidized. So iron is the oxidizing agent. Copper is the reducing agent. Just think, whatever, to remember it easily, whatever's happening to that element, it's the opposite agent. That's why it's working for the other side. It's secret. So here, oxidized, reducing agent. Got it? Now, before I go forward, why would copper be oxidized while iron be reduced? Why is that a spontaneous thing to happen? Why doesn't it happen the other way? Well, there's something called a reduction potential. So the tendency for a species, remember when I say species, I mean thingy, right? For a thing, an element, a substance, to gain electrons or be reduced is its reduction potential. And so what we're doing, what we've done is you can't intuitively say, oh, this one has a higher standard reduction potential than something else. They had to experimentally determine standard reduction potentials. And they did it a long time ago when they didn't have a lot of things in lab. And what most labs had was hydrogen gas, an acid, all right? And what they did is they made an electrochemical cell. Do you guys remember that? It's a battery, right? But what we're doing is we're totally separating the oxidation and reduction. And that where the oxidation part would be what's happening to hydrogen. Hydrogen will be oxidized from hydrogen gas to hydrogen ion. And whatever we were experimentally determining the reduction potential of, we'd put where the reduction would be happening, and we'd read whatever the voltmeter would be reading. And that would be the standard reduction potential. And the end product here is that if your substance has a higher reduction potential, a more positive value, it's going to oxidize those substances with lower values. It is more likely to be reduced than things that are lower on the list with lower values. So you have to have those values in order to be able to predict what's going to happen. So if we measure, not against the sheet, but if we measure the voltage for, instead of couple, you can write electrochemical cell, the copper being oxidized and the iron being reduced, the voltmeter reads 0.62 volts. We can use these standard reduction potentials to predict what's going to happen. So the way we got what's in these tables that we're going to look at, we have in a few slides, the way we got those values is to make the oxidation or the anode the standard hydrogen electrode, and the part that we're measuring the value, the reduction or the cathode. And then we just, whatever the voltmeter read, we put on that table. And we can use the values on the table to predict what's going to happen. So here we have a few things going on. This is a picture of a very primitive electrochemical cell. We've separated the reduction and the oxidation. And the electrons are going to flow from whatever's being oxidized through the voltmeter, so we can read how much charge is going through, and then we can go and supply what's being reduced. So you can't just have an oxidation, you can't just have a reduction, you have to have them connected. And so between the sulfurage and the wires, we're connecting them. Just the only way we're connecting them is the electrons. So if you look at the table, you see the table in the back of your book or in the internet. You see a half reaction, the reduction half reaction, and it has on the table 0.77 volts. And what does this not mean, this little circle here? Does anybody remember? Standard conditions. Standard conditions are 1 molar concentrations, 1 atmosphere of gas. Are we at 1 molar concentrations in our cell? No, let's hope not, right? So we're going to take the values that we get off the table with a grain of salt. We'll talk about that later, but it does do a nice job of helping us. All right, and if we look at the reduction potential for the half reaction that's happening here, we see a value of plus 0.15 volts. But is this what's happening on this anode here? These aren't equal, right? What's different between this and this? It's backwards, right? So this is an oxidation, where this is a reduction. So we can predict what's happening on this voltmeter by taking this and reversing it. When you reverse a reduction to oxidation, you're going to change the sign on the standard reduction potential because it's oxidation. The opposite's happening. So what we're going to do is then we're going to add the two. You're going to add the reduction potential for the whatever's being reduced, and then you're going to add or really subtract the reduction potential for what's going to be oxidized. So we can predict that our voltmeter, if we have 1 molar concentrations for all these ions, should read 0.62 volts. Why do we care about that? Why do we care about these standard reduction potentials? Well, as you remember, spontaneity can be related to cell potential. Do you guys remember this? The F is Faraday's constant, N is number of electrons. You guys remember this from Chem 2? If you don't, just take my word for it. Delta G equals negative constants times the cell potential. So what kind of cell potentials would result in a spontaneous delta G? Positive or negative? Oh, wait a second. Positive. So positive cell potentials result in a negative delta G because it's negative right here. Positive cell potentials result in a spontaneous reaction. So if we look at this guy, we calculated positive 0.62. So this reaction where iron gets reduced and copper gets oxidized is spontaneous. Right? Is that good? You guys remember that? Starting to come back? Maybe? No? Yes?
Here's a quick question. Why are they, for the copper, why are they switched?
Because you can't. So this is what's actually happening in this beaker and in this beaker. You can't have two reductions happening. You have to have an oxidation and a reduction. So right here, iron's getting reduced and copper's getting oxidized. But the table in the back of the book only has reductions.
Oh, okay. I missed
So it's called a standard reduction potential. So the information in the back of the book will be a standard reduction potential as a reducing. So that's not being reduced. That's being oxidized. So here, this is going to be switched in its sign because it's not a reduction, it's an oxidation. So sometimes people
do that for every scenario, right? Just switch the sign.
just switch the sign. Yeah, that's right. Or some people say take what's happening as a reduction and then subtract what's happening for the oxidation because that's really switching the sign. So positive cell potential, negative delta G. That, from this, you will know that electrons will flow spontaneously from something that has a more negative standard reduction potential to something with a more positive standard reduction potential. This little prime means pH 7. F is Faraday's constant. You don't need to know. I'm not going to have you do any calculations with this. F is Faraday's constant. N is number of electrons. We are not going to do any calculations. The only thing I want you to know from this is that a positive cell potential results in a negative delta G, which is spontaneous. So those electrochemical cells with a positive cell potential, that's going to be a spontaneous reaction. Negative delta G. Negative delta G is spontaneous. So that's how we're going to know where the electrons are going to go from. So what they've done is these complexes are just globs of proteins and enzymes. They're just globs. So what some poor graduate student did is they took the glob and separated out what was in the glob. And then they said, okay, we have these 5 things in this glob, this complex. How do I know where the electrons are going? They're using standard reduction potentials to predict where the electrons are going. Isn't that awesome? That something that you learned in general chemistry has a real application. See, this is why I love teaching this class, because all those things that people learned in general chemistry, you'd say, I will never use this again. Why did I have to learn this? I'm a bio major. Why am I taking general chemistry? Well, this is why. Because you need to know those.
I have one question.
Sure. What's your question?
For the slide E, it was 0.62 volts. You're saying that's spontaneous?
This is spontaneous. This reaction, as written, is spontaneous. Because if you add these two half reactions. Because the iron is being reduced and the copper is being oxidized. So what we said in the next slide, electrons flow spontaneous from something with a more negative standard reduction potential to a more positive standard reduction potential. So let's take a look at this. This is plus 0.77, and this is plus 0.15. If I just said I have copper 1 and 2 and iron 2 and 3, what's the reaction that's spontaneous? Well, you could say, I'm not going to ask you that on the test. Okay, I'm not going to ask you. But say I asked you 3 years down the road and I just see you at Chili's and I come up and say, how would you know? So, so you would know here it's plus 0.77. Here it's 0.15. 0.77 is more positive than 0.15. So electrons are going to flow from, see how the electrons flow from the copper side over to the iron side. So the smaller number or more negative number is going to be oxidized while the more positive number is going to be reduced. It's a standard reduction potential. The higher the value, the more likely it's going to be reduced. The lower value, the more likely it's going to be oxidized. How many people remember this? People don't. They don't. This is how many of this is like, I never learned this before. You learned it before, but you don't remember it. Okay. All right. Is it coming back to you a little bit? Maybe? Okay. Well, I'm giving you what you need to know. So this is what you need to know. So spontaneous reaction, of course we know. Negative delta G is spontaneous. But now with the standard reduction potentials, cell potentials, positive cell potential. Really, I mean, put a star on this one because this is what we're taking home with this. This is what we're going to carry on from this part. All right, you guys get a break.